So in this video, I'm going to talk about what procedural programming is. I'm going to talk about what object-oriented programming is. I'm going to talk about what object-oriented programming is good for. It must be good for something. It gets a lot of press. I'm going to talk about the sort of basic idea, the most sort of classic idea of what object-oriented design is. And I'm going to end with a cautionary note that maybe there's sometimes too much of an object-oriented thing. We're not going to look at any code in this video. I'm just going to talk about object-oriented programming. So let's start with the thing that came before object-oriented programming, which is procedural programming. And procedural programming is what we've been doing this whole time in this course and in the previous one. In procedural programs are structured as a collection of methods. Methods call each other, and then they pass around a bunch of data using arguments. The arguments are passed in. The methods do some manipulations on those parameters. Maybe they produce some side effects. Maybe they produce some values. Procedural programming is great. People did procedural programming for a long, long time, and they still do. But the problem is that as programs grow to the sort of industrial scale of millions and millions of lines of code that modern programs use, it gets harder and harder to manage those thousands and thousands of procedures. And passing all of the data around that you need as arguments becomes really, really tedious. So object-oriented programming is an effort to solve some of these problems, right? It's another technique for structuring programs. It's very similar to procedural programming. The basic idea is that programs consist of objects, and those objects use each other to perform tasks, right? So that sounds a bit like procedural programming, where we have methods that use each other to perform tasks. Objects are instances of classes. So you think about a class of objects, right? Like, say, mammals are a class of objects, right? There's a bunch of things in the world. Some of them are mammals, right? Those mammals all have something in common, right? They all have hair and give birth to live young. Newspapers are a class of objects. There's a bunch of objects in the world. Some of them are newspapers. None of the ones that are newspapers are also mammals, and they also have properties that are in common, right? So each individual object is an instance of some class in object-oriented programming. So let me talk a bit more about what I mean by a class. You know, if we're talking about a class in the sort of abstract sense, then it's something like mammals or newspapers or something like that. In the programming sense, you can think of classes like that. Another way to think about them is that a class is a piece of code that is a blueprint for how an object is going to be created and how it's going to work, what data is going to be associated with it. Now, one of the problems, one of the principal criticisms of object-oriented programming is that the concept count is absolutely enormous. The number of words that you need to know the definitions of and the relationships between them for object-oriented programming is much, much larger than it is for procedural programming. So we're going to spend the next many episodes of this course on just picking a word in object-oriented programming and delving into what it means. But before we do that, a fun fact about object-oriented programming. The term object-oriented programming was invented by this guy, Alan Kay, who was born in 1940, famous computer scientist. He was the lead for the design of a computer programming language called Smalltalk, which was the first truly object-oriented programming language. All right, so why do we have object-oriented programming? Well, large-scale software is really complex. And why is it so complex? Well, there's a bunch of different causes for complexity, and these are just three of the big ones. The business domain is really complex. People write software that has to deal with the world, and the world is full of all kinds of stuff, right? And that stuff is complicated, and we need to deal with it. You know, just dealing with things like when is it daylight savings time, right? Somebody has to write software to deal with that. Well, the rules for when it's daylight savings time at any point on the globe are very complicated, right? And all of that complexity gets embedded in software somewhere. There's also complexity in the human resource management problems of building that complicated software. When I was at Microsoft, there were literally thousands of people working on Visual Studio. And all of the work of those people had to be organized somehow. All of that work, all of those people needed to be not stepping on each other's toes. They needed to know that if one team promised to deliver some piece of software, that another team that depended on it could use it in a timely manner and that it would work. There's all kinds of human resource management problems like that that become very, very complicated to solve in a world where everything is procedural. And finally, we live in a world where user requirements change all the time. Software needs to be built so that you can say, well, this is working for the user today, and they're going to want more features tomorrow. I'd better be able to add new features, fix bugs, do all of the stuff that users expect of me. And that can be difficult to do in procedural programming. And it adds complexity. So for all of these reasons and many, many more, modern software, very, very complicated in the large. So how does object-oriented programming help us tame this complexity? Well, there's a bunch of ways that it does it. I'm going to go through a few of the principal ways. Kind of the main one that I think about is the idea that object-oriented software takes a bunch of this complexity, it abstracts it away, it encapsulates it into a class, and it says, here is the bits of this class that are for public consumption. Here are the bits of this class that are private implementation details, hands-off. We're the ones who get to understand this information. The people who are using this code do not get to understand this information. They must treat it as a black box that just does the thing that we say it's going to do. Right? And by doing that, you very clearly draw walls around what you can and you can't do. And the example that I like to use is Netflix. If you've never used Netflix, it's an online video service. You don't have to be a computer programmer to use it. It's entirely built out of software, but you don't have to be a computer programmer. You just use the user interface, and it surfaces up to you all of the stuff that you need to do in order to use the system. All of the other complexity of how they manage to get the latest episode of Doctor Who onto your computer, that is never seen by you. Right? But think about how the code that runs on Netflix's servers is organized. There's some piece of code there that's saying, hey, you watched Doctor Who. You might enjoy watching Battlestar Galactica. And that piece of code, that's sort of its own business domain, right? That's its own thing. It knows how to do that. It doesn't need to know how the piece of code that was written by the guy in the next cubicle over that does the billing system works. You could imagine what would happen if the code that made movie recommendations somehow started to take a dependency on the details of the billing system while the billing system was changing, right? It would mean that you couldn't change the billing system without breaking the recommendation engine, and that would then make for a bad user experience. It would make for extra expense for Netflix, be just badness all around. Right? So this idea of encapsulation and of information hiding is a sort of a key tenet of object-oriented programming. This idea of there's some information over here that's mine, and there's some information over here that I'm willing to share with you, and you only get to see the information that I'm sharing. So this is good because it allows separate teams who don't need to know anything about each other's implementation details in order to get value out of each other's software. The other major tenet of object-oriented programming is composition. This is another one that is super, super important, and that is basically that we divide and conquer in order to win. If you have a complex object that does some complex thing, how do you build it? You build it out of simpler objects that do some simpler thing. How do they do their job? They are built out of even simpler objects, and they are in turn built out of even simpler objects. Until we get to, it's got to stop somewhere, until we get to things like integer. Right? There's no decomposing an integer into something that is simpler than an integer. It is what it is. Or string. Right? Well, you could decompose a string into a bunch of characters. So I suppose string is maybe not the bottom. Character is the bottom there. But the point is that we build up and up and up and up and up. We all stand on the shoulders of giants. We compose new solutions out of old solutions. And then the third sort of pillar of object-oriented design that I want to talk about today is inheritance and a closely related idea of polymorphism. So the idea of both inheritance and polymorphism is simply, you got a bunch of user interface elements, right? Maybe you've got buttons and text boxes and labels and date pickers and all of these things. They are all kinds of user interface elements. And so the idea of inheritance is that if you have some bit of code that is common to all of those things, then you put it in one place, and then you share it amongst all of those things. So the code gets reused through a mechanism of inheritance. You say, we have this one kind of thing, a user interface element. It has some code. We create another kind of thing. A button is a kind of user interface element, so it gets to use some of that user interface element's code. Then the idea of polymorphism is to go kind of the other way. Suppose we have some code that needs to consume a user interface element. Well, a button is a user interface element, so I can give it to it. A text box is a user interface element, so I can give it to it. If I have some piece of code that consumes documents, then I can give it expense reports. Expense reports are a kind of document, right? So the idea of polymorphism is, well, just what it says in Greek, right? Polymorphism, many forms, right? So you can have one kind of thing that takes on many forms. OK, so those are kind of the three major tenets of object-oriented design. And I know this is all very highfalutin and abstract, and we will see how this works in practice over the next several videos. So what's the basic design technique for object-oriented programming? Well, programs solve some business problem, and I have business in quotes here because it doesn't need to be a papers and paychecks kind of problem. It could be the robots and aliens and zombies that are in a game, right? The business of the game is making sure that the robots and aliens and zombies all have the right behavior. So what I do when I'm beginning a new object-oriented design is I just write down in a document, somewhere in a note, in OneNote or something like that, I just write down all of the things that I care about in the business domain and what their unchanging relationships are. Right? So I might say, well, an expense report is a kind of document that has an approver. OK, well, those are three things: expense report, document, and approver. And the relationships between them. There's an is a kind of relationship, and there's a has a relationship. Right? Expense report is a kind of document. An expense report has an approver. And then I might go further. I might say an approver is a kind of employee. Right? An employee is a kind of person, and so on. So figure out what all of the things are in that domain and what all of the unchanging relationships are between them. And this is kind of a key point. Is that those relationships have to be unchanging, because in object-oriented design, we often end up making choices that assume that one set of relationships are not going to change. Encoding something like tax policy into an object-oriented system is maybe not a good idea, because tax policies change. Right? The fact that tax policies are about purchases, right? That doesn't change. That's the kind of thing that you want to encode into an object-oriented system, but not what the specific policy is, because that's one of these complicated human things that's going to change over time. So you then design a bunch of classes that encode these relationships, and then you implement the classes. That's sort of the basic object-oriented design. And this is kind of a novice way to think about object-oriented design. There is a very deep theory of object-oriented design and design patterns, and I'm going to go into hardly any of that in this course. So object-oriented programming, is it amazing or is it awesome? Is a question I am often asked, and a little bit sarcastically. I always try to remember that object-oriented programming is the means, and it is not the end. Right? The software that satisfies the desires of its users is the end. Object-oriented programming is just how I get there. It's very easy, particularly for novices at object-oriented programming, to believe, well, having really good object-oriented style is the end. No, it's not. Right? It is the means to achieving the end at a reasonable cost. Object-oriented programming is, believe it or not the best technique for all possible problems in all possible domains. And finally, and I'm going to come back to this point many times in this course, because I think it's really important, do not go crazy with inheritance. People all the time get what I call object happiness disease, where they start saying, OK, well, I've got a program that worries about animals. And I'm going to have to build this class hierarchy where I need to encode in it that, well, there are mammals, and mammals are a kind of animal, and giraffes are a kind of mammal. And so, well, wait a minute, giraffes have hoofs. So maybe giraffes are a kind of ungulate, and ungulates are a kind of mammal. And then you start to worry about, well, wait a minute, what is a platypus anyway? I mean, platypuses are mammals, but they lay eggs. And No, it just gets to be a big mess. Not every is a kind of relationship needs to be modeled. Not everything needs to be done through code sharing through inheritance. Very common for people to overuse that. And like I said, we'll come back to this point. So, summing up, I know that was a lot of verbiage in a small amount of time, and we're going to explore each of these concepts in much more practical detail. Object-oriented programming structures programs as collections of classes. Classes are blueprints for objects. Objects use each other's methods to perform computations. And object-oriented programming, the entire point is there is large-scale software out there that needs to be constructed. It's going to be complicated. We need to tame that complexity through techniques like encapsulation and composition and inheritance.